All right, we're back. Time to answer our questions. So we've got the spectrogram of
Where were you a year ago?
and the question was, why do we have these horizontal gray lines stacked on top of each other? And the answer is that these are the harmonics of the complex sound. So just like we saw in that overtone singing or throat singing example, we have kind of layers of harmonics stacked on top of each other, but we can emphasize particular harmonics or particular frequencies, make them more intense to get different qualities of sound. So what's different here than what we saw with the overtone singing example is that for overtone singing, the goal is to keep your F0 flat, as monotone as possible, and that makes the harmonics the same frequencies at all times. And so you can kind of just focus on a specific frequency that you want to emphasize and get a specific harmonic out of that. This is a little more complicated than that for two reasons. One of which is that this guy's F0 is changing over time.
Where were you a year ago?
So it kind of goes up and down. When it goes up, these harmonics should be more broadly spaced apart from each other. When it goes down, like it does at the tail end of this, they get closer and closer in the frequency scale, so they get more packed down here at the bottom. For high frequencies, they're more spread out, like around here. On top of that, if you remember from the overtone singing example, that singer was able to focus in on a specific frequency or harmonic for a short amount of time and then move on to the next one. But it's still his sort of emphases were a lot longer in time than we normally see in speech. So here, the frequency or the intense frequencies are changing quite rapidly, like especially the second one, which corresponds to that whistle we heard before on the last video.
Where were you a year ago?
You can't hear it as such when you listen to that speech sample, but it bounces up and down really quickly, and it spans a quick range of like 8 or 10 different harmonics as it goes up and down. And then those specific harmonics will change depending on what the F0 or the fundamental frequency is. I'm getting a little ahead of myself now, just to let you know kind of just how complex things are. So let's take a step back now for a second and think about, well, how exactly are we emphasizing certain harmonics? How are we making certain harmonics more intense than others? And the way you do that is that you take advantage of this physical phenomenon known as resonance. So you can use resonance to amplify, make louder specific harmonics, or you can dampen them as well, make them less loud in a speech sound. So what is resonance? Resonance is basically when one physical object is set in motion by the vibrations of another object. So you can think about this conceptually. Let's say I have a object over here, which is just vibrating back and forth in space, and eventually there's another one in its vicinity which starts to vibrate back and forth at the same frequency as the original one. And when that happens, the two of them together are going to be more intense than just the one by itself. It's going to amplify the sound that's originally being made by the original motion. Okay, so a resonating object is going to reinforce, I can't do this very well today for some reason. A resonating object reinforces sound waves at particular frequencies by vibrating at those frequencies itself. And what's happening is that this initial motion is pushing sound waves back and forth, is pushing little air molecules or shooting waves through those air molecules so that another object will kind of respond to those sound waves by vibrating at the same frequency at more or less the same time. So again, the moral of this is that resonance is going to make sounds at those particular frequencies louder. Okay, so resonance is something we find pretty much everywhere in the physical world. A basic example, unfortunately I don't own a tuning fork, I probably should, is a tuning fork. So if you smack a tuning fork, basically what that does is kind of send a shock wave of all frequencies through the tuning fork, and then there's one that it likes, that it will resonate at, so it kind of hangs on to that one, and you'll just hear that pure tone for a short amount of time after you hit it. The bodies of musical instruments resonate, so that's kind of why they're there. In a violin or a guitar or a piano, you voice the instrument by, say, plucking a string or bowing a string or hitting it with a hammer. So that creates the initial sound, but then the body of the musical instrument will resonate in response to that to give you kind of a different quality of sound. So you can play the same note on a violin as you play on a guitar, but it's going to sound different in part because those two instruments will resonate at different frequencies. You can blow across the mouth of a bottle. I've got one here. Let's see if I can actually make this work. a little bit. But when I'm blowing across the top of the bottle, I'm again kind of creating turbulence at a wide range of frequencies. And then this is the part of the bottle that will actually resonate in response to that. Kind of thinking in a different way as opposed to sound, you can also think of maybe like pushing somebody on a swing. Like if you want to push your kid, sister, or brother on a swing for a while, you push them once, and then there's a response in the object in response to the initial sort of action that you place, or initial sort of force that you push into your kid, sister, or brother on the swing. If you keep pushing, they will keep swinging, and that's basically a form of resonance. You just need to put a little bit of energy into the system, and you kind of get a bigger payoff from that. But there's one motion, which is the motion of your hands pushing, and there's a second motion of the kid actually swinging on the swing. Your bathroom walls tend to resonate pretty well, especially if they're not like carpeted or muffled for some reason. So this is often a reason why people like to sing in the shower, because they get that nice reverb, like the reverb we're getting on these example sound files when I play them in this recording setup. So this is something we find everywhere around us in the physical world, because we're kind of always almost always surrounded by objects that will resonate in response to whatever sounds we're making or sounds that we hear in the world around us. In the case of speech, what we actually care about, what's resonating, is primarily your mouth and then sometimes your nose. So you can think of this a little bit like a musical instrument. Like these are the strings of your violin or guitar or piano. Your vocal folds down here are kind of creating the initial noise. And then the body of your instrument is up here. It's in your mouth and maybe your nose, depending on where the airflow goes. And that is going to vibrate in response to the vibrations you initially create at your vocal folds, and it's going to emphasize some of the vibration, some of the frequencies of the vibration down here more than others. And this is what's resonating. Okay, so objects will resonate at specific frequencies depending on what they're made of, what their shape is, and what their size is. And to kind of skip ahead a little bit, the way we get different frequencies to resonate in speech is kind of by changing the shape and size of our vocal tract as we speak. But first things first, to kind of give you the basic correlation, you can think about another musical instrument, a pipe organ. And a pipe organ has a series of pipes, all of which play different notes when air blows through them. So the larger tubes are going to resonate at lower frequencies, and then the shorter or smaller tubes will resonate at higher frequencies. That gives you sort of the range of notes you need to play in music if you're playing an organ, if you're so lucky to do so. So how does resonance occur? So normally, we talked about sine waves a couple weeks ago, but normally a sound wave or any kind of wave is going to just travel through a medium indefinitely. I guess the extremist example I can think of is like electromagnetic radiation sort of traveling through space indefinitely, but let's not go there. It's a little complicated. A little less complicated, we can think of what happens when you throw like a pebble or a stone into a pond. It'll make sort of an initial splash, and then the water will bounce up and down in response to that. And it will travel outward from where you threw the stone in the first place, from its impact point, all the way across the pond until it gets sort of to the edge of it. We'll talk about what happens at the edge of it on the next slide, but until it gets there, it's what is called a traveling wave, so it's just kind of moving without having to worry about anything getting in its way. Once it hits something, though, then you get a reflected wave. And then what happens to the wave then depends on what kind of resistance the wave encounters. If the wave meets a hard surface, it's going to get a true bounce. So we talked before with sound waves, we get compressions and rarefactions. So compressions are areas of high pressure in the sound wave where lots of molecules are kind of jammed up against each other. Rarefactions are where they're spread apart from each other, so there's not many molecules in the same space. We know sound waves alternate back and forth between areas of high pressure and low pressure. When an area of high pressure hits a hard surface, it's going to bounce back as an area of high pressure. Compressions come back as compressions. Rarefactions also come back as rarefactions. So if you want to think about this at a very simple level, actually I'm not even going to give that demo because it's not worth it. But I'll give you another example, which is borrowed from the textbook, which is that of sound in a closed tube. So let's say you have a kind of unusual setup. The only place I've ever really seen this is in a phonetics lab. But let's say you happen to find yourself so lucky to be in a phonetics lab, and there you find a professor who has, for some reason, taken a long plastic tube and put a loudspeaker at one end of it. And so what you can do is that this tube is filled with air molecules, and you could, with this loudspeaker, send a pulse of air through the plastic tube. So this loudspeaker will kind of push, like pushing a kid on the swing, and that will create a compression of air molecules next to the loudspeaker, which, because it's traveling for now, will travel down the length of the tube until it gets to the far end, which is closed. I forgot to mention that part, but we have a closed tube at the far end. And the air molecules will kind of bunch up at that end, but then also the wave will bounce back. So this compression travels down the length of the tube, bounces, and comes back the other way until it gets back to the loudspeaker. Something which you may notice in this diagram is that as soon as I push this wavefront of molecules down the length of the tube, behind it, what happens is that I get a rarefaction. So if the air molecules are all kind of bunching up down at the far end, at this end there's not as many air molecules left, and I get a rarefaction. And then what happens is, as this one comes back, they kind of trade places. So the compression travels down this way, bounces, comes back, but as it creates this rarefaction is also going to travel down the length of the tube and bounce itself at the far end and come back too. That isn't included here at in the continuation of this, but one thing to notice is that when they're kind of meeting in the middle, the rarefaction going this way, the compression coming back to the loudspeaker, they balance each other out. So at this particular moment in time, it looks like nothing is happening. It's basically the same as what we started with, but then they switch places and then they'll just keep doing that, right? Okay, so let's think about this. Let's say we have in this sort of setup at the far end of the tube, we have put a microphone which can measure how air pressure changes over time. So this is a waveform. This is our air pressure or amplitude here, and this is time in the x-axis. So this microphone is measuring that air pressure will increase as that initial compression goes down the length of the tube, and then as it bounces, that compression is going to go back the other way, and what's going to happen is that rarefaction will come in and take its place, right? So another way you can think about this is if you go back to the swing analogy. So when you put a kid on a swing, initially it's sort of at that equilibrium point. But let's say you're pulling them back so you can get things started. So towards you, their position increases, and then you kind of push them or let them go, and they go far away from you towards the other end of the pendulum there. So what happens if, say, I'm not just going to push air molecules with the loudspeaker once. I'm not just going to push the kid once, but instead, in both of our analogies, we've got air pressure building up, then the rarefaction comes in, and then the compression comes back again. What happens if, when that initial pressure pulse comes back to the loudspeaker, I push again? Or if, say, I push the kid on a swing, they go that way and they come back, and then I push again. What do you think will happen to our sound wave, or what used to be a traveling wave? Answer in the next video.